November 10th, 1944. The skies above Ormoc Bay, Philippine Islands. Commander David McCampbell ended the war as the Navy's leading ace with 34 kills, all achieved flying F6F Hellcats. 21 of those victories came in the final months of 1944, when he was flying F6 F5 seconds, equipped with war emergency power. Whether the water injection system made the difference in his victories is impossible to prove. McCampbell was an exceptional pilot who would have been successful in any aircraft. But when asked years later about the F6 F5's capabilities, McCampbell noted that the emergency power gave him confidence to engage enemy fighters in situations where caution might have dictated disengagement. Confidence matters in combat. The pilot who knows his aircraft has reserve capability to handle unexpected situations, fights differently than the pilot operating at his machine's limits, with no margin for error. The F6F Hellcat remained in frontline service through the war's end, then transitioned rapidly to training units and reserve squadrons as jets replaced propeller fighters. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By 1954, the last Hellcats were retired from active Navy service. The aircraft that had dominated the Pacific skies for 2 years became obsolete in less than a decade, a testament to how rapidly aviation technology advanced during and after World War II. But the engineering lessons from the R2-80010W water injection system persisted. Modern turbocharged engines use similar principles, injecting water or water methanol mixtures to prevent detonation and increase power output. Racing engines in multiple categories employ water injection to achieve power levels that would be impossible without the evaporative cooling effect. The technology that seemed too risky in 1942 became standard practice across multiple industries. The human story remains the most compelling aspect. Engineers who solved problems they weren't certain could be solved. Test pilots who verified systems would function reliably under conditions that exceeded design specifications. Maintenance crews who kept complex systems operational under combat conditions. And combat pilots who activated emergency power and trusted their machines to deliver when their lives depended on it. That trust was earned through months of development, hundreds of hours of testing, and the accumulated experience of thousands of combat sorties where the system performed as designed. War emergency power wasn't magic. It was engineering. Careful, methodical, conservative engineering that took a technology initially considered too risky for combat use and refined it into a reliable system that expanded pilot options when circumstances demanded alternatives. The F6F5 Hellcat, with its R2-80010W engine and water injection capability, represented the peak development of piston engine carrier fighter technology in World War II. Faster aircraft existed, more maneuverable fighters flew in other theaters, but for the specific mission of carrier-based operations in the Pacific, the F6F5 combined performance, reliability, maintainability, and survivability in proportions that proved unbeatable, and when pilots needed 5 minutes of emergency power to overcome altitude disadvantages, catch fleeing enemies, or survive situations that should have been fatal, they pushed the throttle forward past the detent and felt the R2-80010W respond with 2200 horsepower of power that had once been considered too dangerous to install. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. David McCampbell shoved his throttle forward past the detent, feeling the F6F Hellcat's Pratt & Whitney double wasp engine respond with a surge of power that shouldn't exist. Not according to the technical manuals. Not according to the engine's rated specifications. The needle on his manifold pressure gauge climbed past 60 inches into territory that would have destroyed an earlier Hellcat's engine in minutes. 20 Japanese Oscar fighters circled 3,000 feet above him, holding altitude advantage, waiting to pounce. In an F6 F3 without war emergency power, McCampbell would have been forced to disengage, diving away from a fight he couldn't win. But this wasn't an F6 F3. This was an F6 F5, and the small toggle switch labeled water injection meant McCampbell could do something that would have been impossible 6 months earlier. He could climb straight into that swarm of enemy fighters and catch them in 3 minutes at their best altitude. The system injecting a mixture of water and methanol into his engine's carburetor had been banned from early Hellcats not because it didn't work, but because Pratt & Whitney's engineers couldn't guarantee it wouldn't destroy the engine after repeated use. Now, after months of testing and refinement, water injection gave McCampbell's Hellcat 200 additional horsepower for up to 5 minutes of emergency combat power. That 5 minutes would turn the tide of the air war over the Philippines, proving that sometimes the difference between victory and defeat isn't measured in years of development or billions in research funding, but in the crucial seconds, when a pilot needs power that doesn't officially exist, and an engine that can deliver it without tearing itself apart. This is the story of how an emergency power system that engineers initially refused to install transformed the F6F Hellcat from a capable fighter into an absolute predator, and how the mechanics and test pilots who pushed the boundaries of what was possible gave American naval aviators the one thing they needed most when facing impossible odds. Options. June 1942. Bethpage, Long Island, New York. Grumman Aircraft Engineering Corporation. Test pilot Robert Lester Hall climbed into the cockpit of the XF6F1 prototype for its maiden flight, and everything about the airplane felt wrong. Not dangerous wrong, but insufficient wrong. The kind of wrong that would get pilots killed 6 months from now when this fighter started facing Japanese Zeros in actual combat. The Wright R2000 600 Cyclone engine sitting in front of Hall produced 1,699 horsepower, which sounded impressive until you did the math against what the Navy desperately needed. Reports from the Pacific indicated the Zero could outclimb and outturn everything America fielded. The Wildcat was getting slaughtered. The Corsair, despite its beautiful lines and promising performance, had carrier landing problems that might never be solved. The Navy needed a fighter that could be produced quickly, operated safely from carriers by pilots with minimal training, and could match or exceed the Zero in the categories that actually mattered in combat: speed, climb rate, and survivability. What Hall was about to fly had 2 of those 3. Maybe. The 25-minute first flight confirmed what Grumman's engineers already suspected. The XF6F1 flew well, handled beautifully, and was utterly inadequate for the mission. The Navy needed more power, and they needed it immediately. 4 weeks later, on July 30th, 1942, Hall climbed into a different prototype. Same airframe, different engine. The second XF6F prototype, now designated XF6F3, carried a Pratt & Whitney R2 80010 double wasp, producing 2,000 horsepower, a 30% power increase that transformed the aircraft's capabilities. The double wasp was already powering the Vought F4U Corsair and the Republic P-47 Thunderbolt, and it was proving to be one of the most reliable and powerful radial engines ever designed. 18 cylinders arranged in 2 rows, air-cooled, supercharged, and built with the kind of robust engineering that characterized Pratt & Whitney's best work. But even 2,000 horsepower might not be enough. Engineers at Pratt & Whitney knew this. They'd been experimenting with a system that could push the R2800 past its rated limits for short bursts, delivering emergency power when pilots needed it most. The problem was that this system violated every principle of conservative engine design that had kept aircraft engines reliable for the past 2 decades. The system was called anti-detonant injection. Engineers called it ADI. Pilots would come to call it water injection, even though the mixture was half methanol. And in mid-1942, when the XF6F3 first flew, ADI was considered too experimental, too risky, and too likely to destroy engines to be installed on production aircraft. Here's how it worked, or more accurately, here's why it worked, despite seeming like it shouldn't. An internal combustion engine's power output is limited by detonation. Push the manifold pressure too high, increase the fuel-air mixture density too much, and the fuel ignites prematurely and uncontrollably before the spark plug fires. The result is called knock, or detonation, and it destroys engines by creating shock waves that fracture pistons, damage valves, and turn precision machinery into expensive scrap metal. Aviation fuel octane ratings exist specifically to prevent detonation. 100-octane fuel can handle more compression and higher manifold pressures than lower-grade fuels. But even 100-octane fuel has limits, and by 1942, American fighters were bumping against those limits constantly. Water injection solved the problem through basic thermodynamics. Inject a fine mist of water-methanol mixture into the carburetor, along with the fuel-air mixture, and several things happen simultaneously. The water component evaporates as it enters the combustion chamber, absorbing enormous amounts of heat. This cools the fuel-air mixture, increasing its density and allowing more fuel and air to pack into the cylinder for each combustion stroke. The methanol component adds a small amount of combustible material, while also serving as antifreeze to prevent the water from freezing at altitude. But the real magic happens during the combustion event itself. The water vapor continues absorbing heat as combustion occurs, lowering peak temperatures and preventing the premature ignition that causes detonation. The result is simple. An engine running water injection can operate at manifold pressures that would destroy it under normal conditions, producing significantly more power without detonating. For the R280010 engine, water injection meant an increase from 2,000 horsepower to 2,200 horsepower. 200 extra horsepower doesn't sound revolutionary until you calculate what it means for climb rate. Those 200 horses could push an F6F from 3,200 feet per minute climb rate to over 3,400 feet per minute. In a dogfight where altitude equals energy and energy equals survival, an extra 200 feet of climb per minute was the difference between catching an enemy fighter and watching it escape. But in mid-1942, nobody was willing to bet pilots' lives on water injection working reliably in combat conditions. The concerns were legitimate. The ADI system added complexity. It required a separate tank holding approximately 15 gallons of water-methanol mixture. It needed pressure sensors to monitor manifold pressure, throttle position sensors to activate injection at the correct power settings, a pressurized injection system to force the mixture into the carburetor, and, crucially, clean injector nozzles that wouldn't clog with carbon deposits after repeated use. If the system activated incorrectly, it could flood the engine with too much water, killing power at exactly the wrong moment. If it failed to activate when needed, pilots would push the throttle forward, expecting emergency power, and get nothing while the engine detonated itself to pieces. If the nozzles closed partially, the engine would run rough, potentially causing pilots to abort missions or, worse, assume their engine was damaged when it was actually functioning normally, except for the ADI malfunction. And there was another problem nobody wanted to discuss publicly. Water injection worked by cooling the combustion process. Cooler combustion temperatures were excellent for preventing detonation, but they also increased the risk of carbon buildup on spark plugs, valves, and cylinder heads. Carbon buildup meant fouled plugs, stuck valves, and engines that ran progressively worse with each hour of operation until major maintenance became necessary. For civilian aircraft or bombers with multiple engines and the ability to limp home on reduced power, these maintenance concerns were manageable. For single-engine carrier fighters operating hundreds of miles from their ships over hostile territory, with pilots whose lives depended on their engines running flawlessly for hours at a time, the risks seemed unacceptable. So the initial production, F6F Hellcats, rolling off Grumman's assembly lines in October 1942, came with powerful, reliable R280010 engines that delivered 2,000 horsepower and nothing more. No water injection, no ADI system, no emergency power beyond the engine's rated limits, and for the first year of the F6F's combat service, that was enough. The Hellcat first saw combat on August 31, 1943, in a strike against Marcus Island, fighting Squadrons 5 and 9, operating from the carriers Yorktown and Independence, destroyed 8 twin-engine bombers on the ground and returned home having lost 2 Hellcats to anti-aircraft fire and 1 to engine trouble. In the air-to-air combat that followed over the next months, the Hellcat proved itself decisively superior to the Zero in most performance categories. The F6F was faster at all altitudes. It climbed better above 14,000 feet, dive faster and roll quicker at high speeds. It carried heavier armament, had far superior protection for pilot and fuel tanks, and could absorb battle damage that would destroy a Zero. American pilots, following tactics developed from studying the captured Akutan Zero, learned to avoid slow-speed turning fights where the Zero excelled and instead use high-speed slashing attacks that played to the Hellcat's strengths. The kill ratio numbers told the story. At the Battle of Tarawa on November 23, 1943, Hellcats engaged Zeros over the invasion beaches and scored 30 kills for the loss of one F6F. The era of Japanese air superiority was ending, and the Hellcat was the weapon that ended it. But combat also revealed scenarios where even the F6F's impressive performance wasn't quite enough. Pilots reported situations where Japanese fighters held altitude advantage, and the Hellcat couldn't climb fast enough to engage before the enemy escaped or repositioned. Scenarios where a damaged F6F needed just a little more power to make it back to the carrier instead of ditching in the ocean. Moments where the difference between catching a fleeing bomber and watching it escape came down to 50 feet per minute of additional climb rate. The after-action reports accumulated through late 1943 and early 1944. Not complaints, exactly, because pilots loved the Hellcat's reliability and ruggedness, but observations that, in certain tactical situations, more power would have changed outcomes, would have saved pilots, would have destroyed more enemy aircraft. Engineers at Pratt & Whitney and Grumman had been paying attention. By late 1943, water injection systems had accumulated enough testing hours on other aircraft to demonstrate they could work reliably if properly designed and maintained. The P-47 Thunderbolt, also powered by the R-2800, had successfully tested water injection. The problems weren't insurmountable. They were engineering challenges, and engineers live to solve challenges. The development program that followed happened faster than any peacetime development could have occurred, driven by the knowledge that every day's delay meant more pilots facing situations where they needed power that didn't exist. Pratt & Whitney designated the water injection-equipped engine as the R2-80010W. The W suffix denoted the ADI system, and that simple letter meant a complete redesign of the engine's accessory section to accommodate the injection hardware. The carburetor needed modification to accept the water-methanol mixture without disrupting fuel flow. New pressure sensors had to be calibrated to activate injection at exactly 60 inches of manifold pressure. The fuel control system required revision to maintain proper fuel-air ratios when water injection was active, and crucially, the injection nozzles needed a design that would resist carbon fouling while delivering a precisely atomized spray pattern that would mix evenly with the fuel-air charge. The testing program ran through late 1943 and early 1944, with test engines running for hundreds of hours under every conceivable condition. Maximum power climbs, extended cruises, emergency war-power operation for 5-minute bursts followed by immediate throttle reduction, cold starts at altitude, high-temperature ground operations, every failure mode the engineers could imagine, they tested. Some problems emerged immediately. Early injection nozzles clogged after 20 hours of operation, requiring redesign with larger orifices and self-cleaning geometry. The methanol concentration needed adjustment. Too much caused rough running, too little allowed freezing at altitude. The activation threshold required fine-tuning so that injection occurred smoothly without a surge or hesitation that pilots would notice. But the fundamental system worked, an R2-80010W running on water. Injection could sustain 2,200 horsepower at 67 inches of manifold pressure for 5 minutes without detonation or damage. 5 minutes was enough for any emergency. Long enough to climb to engage enemy fighters, long enough to escape a bad tactical situation, long enough to coax a damaged aircraft back to the carrier when ditching seemed inevitable. Ground testing gave way to flight testing, with modified F6F prototypes carrying the new engine through demanding evaluation flights. Test pilots pushed the war emergency power system through its limits, activating water injection during maximum performance climbs, during high-G maneuvers. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. During simulated combat conditions where they needed maximum power immediately, the system performed. More importantly, it performed reliably. Engines didn't explode. Nozzles didn't clog after a few hours. The carbon buildup that engineers had feared proved manageable with proper maintenance procedures. The R2-80010W was ready for production. In April 1944, Grumman began producing the F6F5, an improved Hellcat incorporating the R2-80010W engine, along with other refinements. Externally, the F6F5 looked almost identical to the F6F3. Redesigned engine cowling slightly more streamlined, new windscreen with integral bulletproof glass, spring-loaded tabs on the ailerons for improved control response, strengthened tail surfaces. But the real difference was invisible. Inside that cowling sat an engine with a water methanol tank, injection system, and the ability to deliver 2,200 horsepower when a pilot needed it most. Production ramped up with Grumman's characteristic efficiency. By June 1944, F6F5 seconds were reaching fleet squadrons, replacing earlier F6F3 seconds on the major carriers. Pilots received briefings on the new war emergency power system, with specific emphasis on when to use it and, critically, when not to use it. The 5-minute limitation wasn't arbitrary. Running maximum power with water injection for longer than 5 minutes risked overheating the engine, even with the cooling effect of the water. The operating procedure was clear. War emergency power for emergencies only. Activate the system, use the power, reduce throttle back to normal maximum as soon as the tactical situation allowed. And then came the test. November 5, 1944, the Philippines. Commander Eugene Fairfax led 52 F6F Hellcats from Task Group 38.1 on a dawn strike against the Clark Field complex. The target was approximately 160 miles from the carrier force, and intelligence indicated significant Japanese air strength in the area. The Hellcats arrived at first light, dispersing to attack parked aircraft at Tarlac and Mabalacat airfields. Fairfax's pilots expected minimal air opposition, Japanese fighters having taken heavy losses in previous strikes. But as the Hellcats began their strafing runs, Japanese fighters appeared. Not a few, dozens. The Japanese had been hiding aircraft in revetments far from the actual airfields, camouflaged positions up to 35 miles from the nearest runway, waiting for exactly this moment. Oscar and Tojo fighters, flown by pilots who'd survived the brutal attrition of the past year, rose to meet the American strike. What followed was exactly the type of engagement where war emergency power would prove its worth or reveal its limitations. The Japanese fighters had altitude advantage, having climbed to meet the Americans rather than being caught on the ground. In an F6, F3, the American pilots would have been forced into a defensive fight, using superior speed to disengage and reposition, rather than climbing to engage directly. But these were F6F5 seconds, and when Lieutenant Commander Swope's division found themselves 3,000 feet below a formation of Tojos, he did something that would have been tactically impossible 6 months earlier. He pushed his throttle forward past the detent, activating water injection, and climbed straight at the enemy fighters. The additional 200 horsepower transformed the engagement. Swope's Hellcats, which should have needed 5 minutes or more to climb to the enemy's altitude, reached firing position in under 3 minutes. The Tojos, expecting to control the engagement through altitude advantage, suddenly found F6F5 seconds in their formation with speed and energy to maneuver. Swope and his wingmen each shot down 2 Tojos. The Japanese fighters attempted to use their superior low-speed maneuverability to escape, but the Hellcats' speed and climb rate, enhanced by war emergency power, allowed the Americans to remain in firing position throughout the engagement. Across the sprawling air battle, similar scenarios played out repeatedly. F6 F5 pilots activated water injection to climb rapidly to enemy formations, using the temporary power boost to close altitude disadvantages that would have been insurmountable in earlier Hellcats. The Japanese pilots, experienced with the standard F6 F3's performance envelope, found themselves facing fighters that climbed faster and accelerated harder than they'd been trained to expect. By the end of the engagement, the Americans had shot down 25 Japanese fighters. VF-11 from the Hornet alone claimed 13 kills, including 7 Tojos and 6 Oscars. American losses were light. The combination of superior aircraft, sound tactics, and the emergency power that allowed pilots to dictate engagement terms had created a one-sided victory. But the real validation of war emergency power came 5 days later, when Commander David McCampbell faced a scenario that tested the system's capabilities against the most basic question. Could an F6 F5 using water injection catch enemy fighters at their optimal altitude when starting from a significant disadvantage? November 10th. McCampbell, flying as commander of Air Group 15 from the USS Essex, led 16 Hellcats on a convoy strike near Ormoc Bay. Japanese Oscar fighters rose to intercept, approximately 20 aircraft climbing to 11,000 feet, their optimal altitude for maneuverability and performance. McCampbell's F6 F5 seconds were at 8,000 feet when the enemy fighters reached position, giving the Japanese a 3,000-foot altitude advantage. Standard doctrine in an F6 F3 would have been to maintain speed, decline combat, and reposition for a more favorable engagement. McCampbell, however, had war emergency power. He pushed his throttle forward, activating water injection. The R2-80010W responded with 2,200 horsepower, and McCampbell's Hellcat began climbing at a rate that seemed impossible for a fighter weighing over 13,000 pounds fully loaded, 3,400 feet per minute. 3 minutes. The mathematics were stark and unforgiving. 3,000 feet of altitude disadvantage divided by 3,400 feet per minute climb rate equaled just under 3 minutes to reach the enemy formation. The Japanese fighters, confident in their altitude advantage, held position rather than diving to attack. They'd learned from bitter experience that diving away from formation to chase American fighters was a good way to get isolated and killed. They'd maintain altitude superiority and force the Americans to come up to them, where the Oscar's better low-speed turning ability would dominate. Except the Americans did come up. In 3 minutes, McCampbell's Hellcat climbed from 8,000 feet to 11,000, arriving at the Japanese formation with speed and energy intact. The Oscars, which had been expecting to control the engagement through altitude advantage, suddenly had F6 F5 seconds in their midst with the tactical initiative. The dogfight that followed demonstrated everything the F6 F5 had been designed to accomplish. McCampbell and his pilots used their speed and power advantages to make slashing attacks, diving on individual Oscars, firing burst, and then zooming back to altitude using war emergency power to maintain energy throughout the engagement. The Japanese fighters attempted to use their superior turning ability to escape, but the F6 F5's speed and climb rate, amplified by water injection, allowed the Americans to remain in firing position or disengage and reposition before the enemy could press any temporary advantage. Fabled 15, as VF-15 was known, shot down 10 Oscars in the engagement, including 1 kill by McCampbell himself. More importantly, they'd done so after starting from a severe altitude disadvantage that should have forced disengagement or resulted in heavy American losses. McCampbell's after-action report contained a sentence that validated everything Pratt and Whitney and Grumman had worked to achieve. It is worthy of note that the F6 F5 with war emergency power was able to overcome a 3,000-foot altitude disadvantage and catch Oscar in about 3 minutes at his best altitude, 11,000 feet. That capability, the ability to climb rapidly enough to engage enemy fighters holding superior position, fundamentally changed the tactical equation. Japanese pilots could no longer rely on altitude advantage to control engagements. F6 F5 pilots had the power to climb up and force combat on American terms. But McCampbell's report also highlighted a growing issue that would complicate F6F5 operations through the end of the war. A significant number of F6F3 seconds without water injection remained in service alongside the newer F6F5 seconds. Some squadrons flew mixed formations, with some pilots in aircraft that had war emergency power and others in earlier models that didn't. On November 5th, during the same strikes where VF-11's F6F5 seconds had performed brilliantly, Ensign WWII, flying an F6F5P photo reconnaissance variant, was attacked by a Japanese Oscar that set his drop tank on fire. Mann's section leader, flying an F6F3 without water injection, couldn't maneuver aggressively enough to drive the Oscar away. The F6F3's standard performance, while excellent, wasn't sufficient to maintain position during the high-G weaving required to provide effective defensive support. It was, as many pilots noted with frustration, bitter to know that F6F5 seconds were being assigned to some operational training units back in the United States, while combat squadrons still flew F6F3 seconds without war emergency power. The newer aircraft were reaching fleet squadrons as quickly as Grumman could produce them, but the sheer scale of the Pacific War meant the process took months. By December 1944, most major carrier air groups had transitioned to F6F5 seconds, but the conversion wasn't complete until early 1945. The distinction mattered in combat, and pilots knew it. The War Emergency Power System also revealed maintenance challenges that hadn't been apparent during testing. The water-methanol mixture needed to be pure, free of contamination that could clog injector nozzles. Carrier maintenance crews developed procedures for filtering the mixture before loading it into aircraft tanks, but the process added time to turnaround operations. Some pilots reported that the water injection system would occasionally fail to activate, leaving them with an F6F5 that performed identically to an F6F3 at exactly the moment when they needed emergency power. Investigation revealed that the activation threshold was sensitive to throttle position, and pilots needed to push the throttle firmly past the detent rather than easing it forward gradually. There were also reports, difficult to confirm but persistent, of pilots removing ADI equipment from their aircraft to reduce weight and mechanical complexity. Whether this actually happened on operational aircraft or was simply rumor is unclear from historical records. What is clear is that by late 1945, with the Japanese fielding diminishing air opposition and the war clearly won, some pilots questioned whether the added complexity of war emergency power justified its benefits. But the combat record spoke for itself. In engagements where F6F5 seconds faced Japanese fighters, the Americans' ability to use temporary power boosts to overcome altitude disadvantages, catch fleeing enemies, or disengage from unfavorable situations provided tactical flexibility that saved lives. The Great Marianas Turkey Shoot on June 19 through 20th, 1944, occurred just as F6F5 seconds were beginning to reach fleet squadrons, meaning most Hellcats in that engagement were still F6F3 seconds. But by the time of the Philippines campaign in October and November, the majority of Hellcats engaging Japanese forces were F6F5 seconds with war emergency power. The kill ratios didn't change dramatically. The F6F3 had already been destroying Japanese aircraft at a 19-to-1 ratio, but the types of engagements changed. F6F5 pilots could accept combat in situations where F6F3 pilots would have needed to decline, confident that war emergency power gave them options if the tactical situation deteriorated. And there's the real measure of success for any emergency system. Not whether it makes every mission easier, but whether it provides options when circumstances conspire to eliminate all other choices. By war's end, over 6,800 F6F5 seconds had been produced, compared to 4,400 F6F3 seconds. The F6F5 became the definitive Hellcat, the version that most pilots flew in combat, the standard against which all other carrier fighters were measured. The R2-80010W engine with water injection proved reliable in service, with no epidemic of engine failures, despite initial concerns about the system's complexity. Pratt & Whitney's engineers had solved the problems that made ADI seem too risky in 1942, and the result was an engine that delivered emergency power when pilots needed it, without sacrificing the fundamental reliability that made the Purser R2000 801 of the greatest aircraft engines ever designed. After the war, when the Navy conducted comparative evaluations of Allied and captured Axis fighters, the F6F ranked at the top in most categories, not because it was the fastest, the most maneuverable, or carried the heaviest armament, but because it combined excellent performance across multiple categories, with genuine ruggedness, ease of maintenance, and the kind of reliability that let pilots focus on fighting rather than worrying about whether their aircraft would function. The War Emergency Power System was part of that package, a capability that worked when activated, didn't cause problems when not used, and gave pilots the confidence that their aircraft had more to give when circumstances demanded it. The broader implications of water injection development extended well beyond the F6F program. The lessons learned from the R280010W informed development of even more powerful engine variants for other aircraft. The P-47 Thunderbolt, also powered by R2800 variants, eventually received water injection systems that boosted power to 2800 horsepower in experimental configurations. The F-4U Corsair, which finally solved its carrier landing problems in late 1944, received the R2-80032W engine in the F-4U-5 variant, with water injection allowing 2850 horsepower in war emergency power. The fundamental technology that had been too risky to install in the XF6F 1-inch 1942 became standard equipment on virtually every high-performance American fighter by war's end. But the human element of the water injection story is what makes it compelling. Engineers at Pratt & Whitney, who worked through the problems that made ADI reliable, didn't receive medals or public recognition. Test pilots who pushed experimental engines to their limits to verify the systems would function in combat flew missions that appeared in no newspaper headlines. Carrier maintenance crews who filtered water methanol mixture under combat conditions, often while their ship was under air attack, did their jobs without expecting thanks. And yet their collective efforts gave American pilots the capability to survive situations that would have been fatal in earlier aircraft. How many pilots came home because war emergency power let them climb out of a bad situation? How many Japanese aircraft were destroyed because F6F seconds could catch them at altitudes where earlier Hellcats couldn't? The numbers are impossible to calculate precisely, but the after-action reports provide hints. Commander McCampbell's November 10th engagement, where he overcame a 3,000-foot altitude disadvantage to shoot down an Oscar, is documented. How many similar engagements occurred without detailed after-action reports? How many section leaders used war emergency power to maintain position while defending damaged wingmen? How many damaged F6F seconds made it back to their carriers on emergency power when an F6F would have ditched? The statistics suggest the impact was significant. F6F seconds, which entered combat in mid-1944 and served through the war's end, accounted for a substantial percentage of the Hellcats' total kills, despite serving for less time than the F6F. Whether this reflected the improved capabilities of the F6F, the declining quality of Japanese pilots by late war, or simply the larger numbers of F6F seconds in service is debatable. What isn't debatable is that pilots wanted the F6F. Given a choice between an F6F and an F6F, pilots chose the aircraft with water emergency power every time. Not because the F6F was inadequate, it had already proven itself as a war-winning fighter, but because the F6F was better in the specific scenarios where better mattered most. The technology itself had broader applications beyond military aviation. Water injection systems would be used in commercial aircraft to boost takeoff power at high-altitude airports. Racing engines would adopt the technique to generate enormous power outputs for short periods. The fundamental principle, using evaporative cooling to prevent detonation while increasing manifold pressure, became a standard tool in the engineering toolkit for extracting maximum power from internal combustion engines. But in November 1944, over Ormoc Bay, when David McCampbell activated war emergency power and climbed 3,000 feet in 3 minutes to catch enemy fighters at their optimal altitude, the broader implications didn't matter. What mattered was that his engine delivered the power he needed, reliably, without hesitation, allowing him to take the fight to the enemy on his terms. That's the real measure of any technology. Not whether it's innovative or clever or represents cutting-edge engineering, though water injection was all of those things, but whether it works when someone's life depends on it working, in conditions that were never part of the design specifications, under circumstances the engineers never anticipated. The R-280010W with water injection worked. It worked in the tropical heat of the South Pacific and the bitter cold of high-altitude combat. It worked when carrier maintenance crews serviced it with limited tools and replacement parts. It worked when pilots activated it in maximum G maneuvers that put stresses on every engine component. It worked when damaged aircraft needed one more burst of power to reach friendly territory. The 7,870 F6F Hellcats produced during the war each carried that capability. Each pilot who flew an F6F had access to war emergency power when circumstances demanded it. And over the Philippines, over Okinawa, over the Japanese home islands in the war's final months, pilots used that capability to survive and prevail in situations where earlier aircraft would have left them with no good options. By the time production ended in November 1945, the F6F Hellcat had established itself as the most successful carrier fighter of World War II. 5,156 enemy aircraft destroyed by US Navy and Marine Corps pilots, a kill-to-loss ratio of 19-1 that remains unmatched, 307 naval aviators who achieved ace status flying Hellcats. The F6F was part of that legacy. Not the whole story, because the F6F had already proven itself before the F6F entered service, but a crucial chapter in the evolution of a fighter that started as a good design and became a great one through continuous refinement. And at the center of that refinement was an emergency power system that engineers had been reluctant to install because they couldn't guarantee it would work reliably under combat conditions. The same system that, once properly developed, gave pilots the options they needed when all other options had run out. The story of war emergency power is the story of engineering conservatism giving way to calculated risk when lives depended on taking that risk. It's the story of test pilots pushing systems to their limits to verify they would function when it mattered. It's the story of maintenance crews keeping complex systems operational under impossible conditions. And ultimately, it's the story of combat pilots who activated a switch labeled water injection and felt their aircraft respond with power that shouldn't exist, climbing to meet enemy fighters with confidence that their machine would give them everything they needed to survive the next 5 minutes. 5 minutes. That's all war emergency power was rated for. 5 minutes of emergency power before the engine needed to return to normal operating limits. In combat over the Pacific in 1944 and 1945, 5 minutes was an eternity. 5 minutes was enough time to climb 3,000 feet, enough time to catch a fleeing enemy bomber, enough time to escape a bad tactical situation, enough time to coax a damaged aircraft back to the carrier, enough time to survive. The forbidden trick that wasn't forbidden, just feared. The emergency power that engineers didn't trust until testing proved it reliable. The water injection system that transformed a capable fighter into a dominant one, not through revolutionary changes but through incremental improvements that mattered in the specific moments when improvement meant survival. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.